Good morning, everyone. Can you hear me?
Yes, good morning.
Good morning. Good to see you all again. We're heading into the third block, the final block for this course. Roland also already did an introduction for you. He also said that we'll, of course, be looking at the exam results for the second interim exam at the moment after it has been graded. So the open-ended questions need to be manually graded. So when that's done, we're able to correct some errors on our part if that were the case. So we had some questions in the mail about the ranking. So I'll look into that, and based on those emails, there are probably a few other options that are correct also. So we'll be correcting those when everything is graded. So and we'll put out an announcement when that is done. So for today, we'll be looking at the correlation. Actually, not just today, but for this entire block, we'll be looking at correlation and mostly regression, and see how we can use regression analysis to get some answers on specific questions about continuous variables. So the way predictors in continuous form predict other continuous variables. So what we've seen in the previous block is that we've used predictors that are categorical. The models we used all were, how would I say it, in one form or the other based on analysis of variance, where we started out with a single one-way independent ANOVA and expanded on those statistical models until we landed at the mixed design ANOVAs. But all of them assume that the predictor is a categorical variable. And what we'll be doing this block is look at the cases where we have continuous predictor variables. So we'll be looking at regression analysis, moderation analysis, mediation analysis, and we'll see how that plays into the into different research schemes. But before we start with that, we'll start with just some basics again about the correlation and the simple regression. This is a bit of a repeat of last year because you've already had correlation and you've already had a simple one-way one predictor regression analysis. What I'll try to do is to frame these both of these in the same way as I framed the ANOVA analysis, namely when we are talking about explaining variance. What parts of variance are we actually talking about? Because also with the regression analysis, it's the same that based on a predictor or multiple predictors, you do an estimation. You create a linear regression model which predicts the outcome on a certain variable. And that is what we're trying to get at. So if that process is the same, then that means that we still have an explained part and an unexplained part. So we'll use that to go into these topics. So for today, we have the correlation. The partial correlation will be added. And finally, we'll dive into the regression analysis. Is that clear?
Yes.
Thank you. Very good. So first off, the correlation. The standard Pearson correlation coefficient, or the product moment correlation coefficient, as you may, which is an indication of how two continuous variables are related to each other. So you've discussed this before in year one. So you can have a positive correlation, meaning that if you score higher on one variable, you also score higher on the other variable. And vice versa. So you could have a positive correlation or a negative correlation, and the correlation is always between -1 and +1, where a value of 0 indicates that there is no correlation. This should be something you know, right? This is not new.
Yeah.
Very good. Okay, so in terms of how this correlation coefficient is calculated, we have essentially two parts. So the first part is the covariance part, as at the top here, the covariance. And essentially what you're doing by dividing by the standard deviation for both of the variables is essentially standardizing your difference scores again. So we've seen this trick done many times before in a basic standardization measure for the Z scores, or for any other scores for that matter. We've seen this happen a lot of times, where we actually have want to know the difference between some variables, but if we don't standardize, that means that well, every time you have a different scale, you have to try to interpret this difference in terms of that scale. So, for example, if you have an IQ scale, then you have a standard deviation of 15 points and 100 as a mean. But if you would have a an assertiveness scale, which is measured on with an average possible value of 15 and going to 30 and 0, then you always have to interpret those differences or those scores in terms of the scale that it's measured on. So the standardization makes it possible to always have the same essentially the same scale to interpret. So you always know that if you have a correlation of exactly 1, you have a perfect linear positive correlation. And if it's a negative 0.5, you have a sense of what that correlation would look like. So if we're looking at, for example, this how the covariance is calculated, we see that we're subtracting the score xi, so the score for some individual here. We're subtracting from that the mean of that group, and for the other, we're multiplying this by the score on the other variable for the same person I, and we're subtracting the mean for the entire variable, and we're summing over every person. So we're starting at I1, so that's the first person, and we're going up to IN, which is the last person in your sample. So what does this mean exactly? So in terms of again, a formula, this doesn't give you a lot of information, a lot of sense of what's going on. So it's always good to try to get a sense of what this visually means. So what I'm doing here is just creating some random data, a random normally distributed value for x and for I, with a mean of 10 and a standard deviation of 5. And what I'm doing here is putting the formula that we just seen into a visualization. So what we're seeing here is an x variable here, and we are having a y variable here, and we see the scores for both these two variables. And what I've also plotted is the mean of x, which is seen as the vertical line, black vertical line here. And I've plotted the mean of y, which is plotted as a horizontal line here in black again. So if you look at a specific individual, for example this one, you see that in terms of the formula, if you're subtracting the mean of x from the specific score of an individual, then we're talking about, again, a distance of the mean for variable x to the actual score of the individual. So we're seeing now that this person is quite close to the mean of x, and we can do the same thing, the same for the y variable. So we could look at what is the mean of y. Well, this is here, and for this specific individual, if we're talking about the difference between his score or her score and the average on the y variable, well, we're looking at this difference, the difference from the score for that person going up all the way to the mean of y. So it's this distance. Does that make sense?
Yes.
Very good. Now, if you multiply these, then we see something happen, because when we are multiplying minus signs, of course, we end up with a positive number. And when we're multiplying positive numbers, we also end up with a positive number. So if my individual score is above the average of y, then this is a positive number. And if my individual score for the x variable is also higher than the mean of x, this is also a positive number. So multiply a positive number by a positive number gets you a positive number. So everything that is essentially on the right side of the mean of x, so that's essentially everything that is on this side, starting from the mean of x, which is this, is positive. And for the x variable and for the y variable, it means that everything that's higher than the y variable, going up from the mean of y, is also a positive number. So we essentially have four quadrants, which two of them will, independent of the size of the value, will yield a positive number. That's in this quadrant, top right, and the bottom left. That makes sense, right?
Yes.
And in the other way, multiply a positive with a negative number, we will get a negative sign. And that holds for cases where either you have a value lower than the mean of x, or a value higher than a value lower than the mean of y. So in the top left quadrant and the bottom right quadrant, all values will be negative. So essentially what this is saying is that if you have a lot of observations where your scores are within the top right quadrant and the bottom left quadrant, then you will have a positive correlation. And if you have more on the top left quadrant and the bottom right quadrant, then your correlation will be negative. So that even means that if you have some strange shape of a correlation where your actual scores are pretty dispersed but go through the mean and pretty dispersed on this side, then you could end up with a very high positive correlation, even though the spread is quite high, and it also yields for the other side. So if you look at this, then you can try to visualize, try to think of in what cases would I get a high correlation and in what cases would I get a low correlation. So could anyone think of when we would get a low correlation? when do you think the correlation will be around 0 or something? Looking at this image.
When it's very close to the intercept, like in the middle.
That's true, but then it's not really an intercept, because when you're talking about the intercept, it's specifically talking about the regression. But if you mean the place where the two lines collide, if you have a lot of observations there, then you would probably have a low correlation. And when, where exactly then would you expect that?
What do you what do you mean? Like where the dots would be?
Yeah.
Well, as close to the middle as possible.
Yeah. So you're saying if all the dots are in the middle,
Yeah.
then you would have a low correlation.
I talked when it's more spread, like when our observations are spread.
And what do you mean exactly with spread?
Like you can find them like everywhere.
Okay, so with spread you mean you find observations that are in frequency equally an amount in the red zones here and there, and also in the green zones here and there. That's what you mean, right?
Yes.
Okay, so you're both correct in the sense that if you would have only scores in the totally in the middle, then you would have a correlation of 0, but that doesn't happen pretty often. The spread is indeed relevant, but more important in your statement is that the spread should be equal across all of the quadrants. So if it's focused, as was mentioned first, then having observations around this center point would result in low correlations, but it's not because it's specifically on the center point. No, it's because your observations would be equally frequent on both 4 of the quadrants, and it shouldn't matter if that spread is pretty close to the means of both of these two variables. It could also be quite large, but the thing is, if you have a lot of observations that cover these 4 quadrants, then your correlation will get low, because what you have, the amount of positive multiplications that you have when you follow this bottom formula would be nullified in a sense by all the negative values that you would have in the observations on the red quadrants. So if you have a lot of observations that are in both, then you would end up with correlation that go to 0. Does that make sense?
Yes.
Okay. So you now have this in front of you. You have a bit of a notion of where the dots need to be to have a high correlation, either positive or negative, or a low correlation, either positive or negative. And what I wanted to do now is see if you based on this knowledge you can play the following game, the guess the correlation game, and I'll also drop this link in the chat so you can have a look at it. And I'll try, based on your guidance, I will try to play this game. So what we're seeing here is a scatter plot, which will have an x-axis and a y-axis, and you will be shown dots, and you have to guess the correlation. Make sense? So maybe a few of you turn on your audio, because I need some input from you based on the following one. Okay, what is the correlation, do you think? Anyone?
Positive.
Yeah, okay, but how much?
Oh.
Point what? 0.8, 0.4, 0.5? Sorry?
0.8.
0.8. Okay, let's try this. Oh, this was okay. It actually was 0.76, so we're close. We'll do the next one again. We can't be off too much. What is it, you think?
0.3.
0.3? I'm hearing also 0.6. Anyone else?
0.5.
0.5.
3.
0.3. Okay, we'll go for 0.3. Oh no, it was 0.5 indeed. We'll go on. This one.
0.6.
0.6. Anyone else agrees? Don't agree? So you have to look at the averages, right?
I would say 0.4.
0.4. Anyone else?
Yeah.
4?
0.5.
0.4. 0.5. Okay. Oh, it was 0.6. Let's keep going. We still have one heart left. This one.
0.
Again. Anyone?
No correlation.
No correlation. Point zero exactly?
0.05.
0.05. Let's try this. Yep. Close. We'll keep going. Again? Which
0.2.
point? Anyone agree?
Point.
Less.
Less.
Yes.
Point one?
Yeah.
Point one. Oh no, it was the 0.2. And we're done. Okay, so you see that it's actually quite hard to see, right? Because it's visually also a bit of misleading that you look at such a graph and you think, well, wow, there's a lot of spread. But if you actually look at the amount of observations, for example, that are in the bottom right quadrant here, they are much less than there are in the bottom left quadrant. So you see it's quite hard to see. Do we have a new high score? Yeah, very good. So just play around with this to get a bit of a feeling of what the height of the correlation means, and especially also with what what such a correlation looks like. Because, well, if you look at this one, it's a correlation of 0.21 actually here, and there are quite a few observations here. So maybe these are more than 100 dots that you see here, and we will go into this. But based on such a correlation, you could actually calculate what the significance of such a correlation is. And well, I once was an advisor for a study where people wanted to look at the predictive value of a language assessment as a precursor for your actual performance on the university. So what they did is they had quite a lot of students in. So before they entered university, had them do a language test, and then they looked at the correlation between the language test and when they were admitted to their studies, how they performed on average in the first year, for example. And they were quite happy because they got a significant correlation between those two. Concluding that all students should have a language test as an indication, as a selection criteria for future performance on their studies. But well, even if we're looking at a correlation like this, such a correlation of 0.21 could very well be significant, especially if you have a very large sample size. But if you combine that with some common sense and look at this graph, this doesn't look like something that is very predictive, because there are also a lot of students that have a high score on let's say the language test, but don't perform as well in their study. So it is always, and I think that is the message to take away from this, it is always important to look at the data, to see what it looks like, and to have some common sense on what's actually going on. And in terms of looking at significance values, we already talked about this extensively. It's not just your decision to reject the null if you have a very low p-value, but it's also looking at the effect size. And if you would also take the effect size into consideration, you would conclude that it's quite low, because the effect size measures that we use are actually in correlational analysis are based on the actual correlation value squared. So that's the same r squared that we have seen in the ANOVAs that we've done. So the main message is, don't be fooled by just the outcome of the test statistic, but also look at your data and try to interpret it. Try to interpret what's going on. Okay. So you can play around with the game later if you want, and maybe we can even match up each other if you'd like. So I'm gonna simulate some data. I'm going to what am I doing here? Anyone?
Simulating
Between IQ and 3.
Yeah, I'm simulating indeed IQ based on
The grades.
yes. So I'm applying a regression model where I set the beta coefficients, but we'll be looking into that in the next part of this lecture. So the two variables that we have are IQ and grade, and those are related by the amount of error that we put into the model, and the beta coefficient that specifies the relation, but we'll go into that later. So we essentially have two variables, IQ and grade, and we want to know what the relation is between these two variables. So we can do we can use the correlation, the Pearson correlation, to get to know what this relationship is. But what I wanted to do is to try to frame this in terms of explained variance, as we've seen in the previous blocks that we've been doing. So what I'm doing is plotting the two variables in the same way as we've done in the previous block, where we have the actual score on the variable on the y-axis, and we have the amount of people on the x-axis. And what we've seen in previous lectures is that I've done the same thing, where I put the people on the x-axis, and I've specified what the mean was, and I've specified what the average was, and then we could determine what the difference was from the average to the actual score. So I've done this here, but what's going on here? Because now I have, well, two groups of lines here. Anyone? What's going on here?
I might be completely off, but wasn't this something like the Simpsons paradox?
No, it's not. It's not per se the Simpsons paradox, because that only looks at a specific selected field. So this is more something to do with scaling and the fact that we essentially have two variables now. We have IQ, which is measured on a scale where the average is 100, and we have grades, which are measured in a scale of 1 to 10, essentially.
They're not standardized, right?
Exactly. They're not standardized, so that means that for one variable we have all high scores for the IQs, and we have the other variable that we have all low scores, somewhere between 0 and 10. So if I want to compare these and I want to determine which part of the variance is explained, then of course I have to first standardize these values. So if I do this and do a simple Z transformation where I look at what is the actual score for a person, what is the mean for that entire variable, and divide by the standard deviation, then I standardize this value. So if I standardize both these variables and make the same plot again, I can end up with something like this. I still have IQ, and IQ is blue, and the grade is orange. So now we still have the people on the y-axis, but we have essentially both the scores. We have the people on the x-axis, and we have both the scores standardized on the y-axis, where blue indicates that it's an IQ score, and the orange indicates that it's a grade. So without even applying a regression model to get to this, or any other modeling, we can already see that, well, if you say that one variable could explain a portion of the variance of the other, well, this looks a bit the same as we've had for the previous analysis that we've done within the ANOVAs. And of course, it's an arbitrary question which variable explains what. And it's also a bit of a misleading statement, the notion and the talking that we do about variance explained by, because it's misleading in the sense that you could think that this means that that there's a causal relation, and there's not, because we're just looking at two different variables where the fact that we have these scores does not determine causality, right? So if we would think of, for example, or look at the IQ scores for, let's take this one, for example. So the blue is the IQ, and the orange is the grade. So in terms of explaining how much of the variance of the grade is explained by the IQ of the person. And for this specific person, we see that, well, about half of the variance for the grade for this person is explained by the IQ of this person. And the same thing holds for this one. Well, where about, I think, 1/3 of the variance is explained by IQ for the grade for this person. And in terms of explaining variance, it's the same thing with we have here as we had with the previous block, that you can overshoot, right? You can have variables that are off even to the other side. So, for example, this one. The portion explained variance of IQ is this part, and what's unexplained is then going from that expected score up the entire way to the actual grade for this person. So we can decompose the variance parts again in terms of the parts that are explained versus the parts that are unexplained. And in some cases, for example this one, the explained part overshoots way down here, but the unexplained part that we're left with is then the distance from this standardized IQ score to the standardized actual grade for this person. So in that way, it's thinking about the correlation or thinking about the relation between such two variables, you see that it's the same trick that is essentially applied in terms of explained and unexplained variance. So this is essentially the most simple, right? Because we don't even apply a linear model, we just standardize, which also means that for each individual, your scores on one variable are different than the other. So where we had, for example, with the ANOVAs that the predicted variable for every individual in the specific group was the average, so it was the same for each and every one. We've seen, for example, in the ANCOVA that we had differences for individuals, and if you apply the same trick with just two variables, you also see that each individual has a different score on essentially a different predicted variable, which is based on the score that he had on that variable. And it is also the same in the sense that where you have with some ANOVA model or even a regression model or any model for that matter, you get an outcome variable. You have an outcome variable, the actual score, and you have a predictive variable. So there are just two variables, one predicted based on the model and the actual scores, which you compare to each other. So if you have two variables that you compare to each other that are actually both continuous variables, well, that's essentially the same as looking at the correlation between these two variables. So what we've seen, for example, in getting to determine the explained variance, is that we just correlate these two and square it, and then we have the proportion, the amount of explained variance in terms of percentage. So it's quite the same in that sense as we've been doing so far. Does that make sense?
Yeah, it does.
Yeah, very good. Now for the actual calculation, so we need all the x's, so all the scores that are gathered on the x variable. We need to subtract the mean of x, and we have to multiply it by all scores for the y. For all the people, subtract it by the mean of that, and subtract that entire sum part. So we have to divide that entire part by the degrees of freedom, and the degrees of freedom are n-1 again. So I'm going through the steps, just getting the mean of the grades, getting the mean of the IQ, then setting up the different scores. So the delta, I call it delta grade. I'm just doing a few steps to make it hopefully more clear. So we're looking at the difference in grade, the grade minus the mean of the grades. We're doing the same for IQ. Delta IQ is equal to all the IQ scores minus the mean of IQ. And the product is the multiplication of that difference multiplied by the other difference. So I could have also put delta grade here and delta IQ here, in essence. So if you sum all of that and divide by n minus 1 by the degrees of freedom, you get the covariance.
Could I just ask, after the sum sign, there's I is 1. What does that part stand for?
It means that you're looking, you're summing over each individual. So let's say that it stands for individual. So we're looking at the first person. What is the score for the first person? Subtract the mean and multiply that by the score for the first person on the other variable and subtract the mean. So it's this sum function essentially says you have to do this, this for all the people in your sample. So this is person 1, this is person 2, this is person 3, up to, well, 50 people. So what it's saying in formula terms, it's saying what is the score on X for this individual and subtract the mean. So what is the score on X for this individual? That's this score, and subtract the mean. That's that one. And we're doing the same for this individual and subtracting it by the mean and multiplying those two. And then we have one person. And we're summing because we're now shifting to the next one until we get to the end. Does that make sense?
Yep, thanks.
Okay. So the thing that might be confusing is the fact that you're seeing, oh, we have a product of grade minus mean grade, where you might assume this to be one number, and it's not, because in the variable grade we have, that's a vector. It's a list of all the grades for all the people that for all the persons people that are in here. So this is a vector, and this is just one number. So we're subtracting this mean for each and every observation in the grade vector, and we're doing the same for the IQ. That's a vector too. It contains all the IQ scores for all these people. We're subtracting the mean, which is just one number. So we get a new vector which has the division essentially of these two, the subtraction of these two. And then if we multiply that, we multiply for each and every individual. So the product here is also a vector with essentially the multiplication of these two parts. And because this is a vector of that multiplication, we can say, well, if we sum all those scores that we have there, what do we end up with? Yeah? Does that make sense?
Yes.
Good. So now we have the covariance part. And the problem, what is the problem with the covariance part? Why not just interpret the covariance?
It's not standardized, so you can't compare it.
Exactly. You can compare it. So it's absolutely possible to compare, but it's just a bit harder because it's not standardized. So the point that I made earlier, you have to know what the scales or the combined scales even, because one scale is on the IQ scale, averaging at 100, and the other scale is at a 1 to 10 scale. So if you multiply that, you get, well, values that are in the thousands. And it's hard to comprehend what the size of the scales mean. So indeed, it has to be standardized to not to be interpreted, but to make it a bit easier for us to interpret. And of course, if we standardize, it is always the same, these differences, which means that we can also do some significance testing on those standardized values. So indeed, the final step that we have to apply is standardize by dividing the covariance by the standard deviation for both x and for y. We must multiply these two. So the correlation that we get is the covariance divided by the standard deviation of grade multiplied by the standard deviation of IQ, and that is a correlation of 0.6207. And I do want to go through all these steps, going through the covariance, just to get a bit of an understanding of, well, what I've been showing here with the plots, to solidify the notion that we're looking at differences at distances of means, and that indicates that you could see this in terms of explained variance, where you have positive values if you see that it's overshot on those variables, and negative if it's the other way around. So it's more about having a bit more feeling of what a value of a correlation essentially means and where it comes from, instead of just saying, here be dragons, I'm looking at the output of the correlation and I don't understand what's going on. So that's the reason why you go through this all. But of course, if you just in R use the core function from correlate, and you put in variable x and variable y, or grade and IQ, then you get the correlation in one go. And what I've done here is I didn't put in the grade, right? So what is this? I didn't put in the actual grade and the actual IQ scores. This is something else.
Standardized.
Exactly. This is the standardized values of the grades and the standardized values of the IQ. And what you can see from this is that the standardization standardization doesn't interfere with the actual relation of the variables. If you scale both variables in the same way, the correlation will also be always be the same, because it scales it down again to having an average of 0 and going out to -1 and +1 as a correlation value. So in the final step, I did the correlation with just the grades, unstandardized, and just the IQ, and we get the same value. So it indicates this correlation. You can just use the core function to calculate this correlation, and you're done. Well, we're not actually done, because we do want to know if such a correlation of 0.62 is actually significant. So in other words, if we assume that there is no correlation, if we assume the null to be true, then sometimes we get a correlation that's this value based on chance. So for example, what I've done here in the simulation part, I simulated the grade as being random normal and consisting of 50 people with a standard deviation of 6 and a standard error of 1.6. I've applied a regression model which actually indicates that there is a relation, but if I would have done the IQ in the same way, so if I would have used the random normal function, the same random normal function for IQ, then in my simulation, the IQ and the grade would be definitely unrelated. There would be no relation between those two. And if you have such a scenario where both your variables are actually unrelated, and you repeat that random sampling a lot of times, then sometimes you find a correlation values that are high just by chance. And this is the same notion as we had with the binomial distribution, that even if you assume your your coin to be fair, it doesn't mean that sometimes you throw 10 times heads. It happens. It doesn't happen very often, but it does happen sometimes. So in that same line of reasoning, we could we see this the same holds for this correlation value. So so what I'm doing here is just again showing what we're doing if we multiply the z-scores and divide by n-1. So this still yields the same correlation value. And here I've shown one more time that multiplying those numbers by positive numbers will yield positive results, and negative will yield negative results. So I'll take it out. So this is our data. We have a correlation of 0.6, and if we look at the averages for grade unstandardized, and if we look at the averages for IQ unstandardized, we see that we have most of the observations within the two quadrant, the upper right and the bottom left quadrant, and we have a few observations also in the top left and the bottom right, but they're closer to the middle. So you could already see that we have a bit of a line. If we would fit a regression line, it could be somewhere in here. Now, if we want to test the significance of the correlation, then we have to go back to the t-test. So what is happening is that we transform the actual correlation value based on or let's say incorporating the sample size to get essentially a t-value. And this t-value is the same t-value as we've used in the first block. So what we're doing is we're saying, well, what is the correlation multiplied by the square root of n-2? So this is multiplied by the square root of the standard deviations. And we're dividing this by essentially the square root of 1 minus the correlation squared. So what does this correlation squared mean again? Do you know?
The effect size?
So yeah, sometimes we use this as an effect size, so that's absolutely true. But in terms of explained, this is the explained variance part. So if we square the correlation, we have the proportion in terms of percentages of explained variance. So R squared means the amount of variance explained. So what would it mean if we state 1 minus R squared?
The unexplained variance.
Exactly. So essentially we're saying what is the correlation that we have scaled to the degrees of freedom divided by essentially the unexplained part. And that gets us a t-distributed a t-value. And for the t-value, the same holds again as did in our t-tests that we performed. We have the degrees of freedom, and we have the null, which states that the t value is equal to 0, or the alternative hypothesis that can have two directions, namely our three options, namely the t-value is not 0, it's higher than 0, or it's smaller than 0 if you want to give it a direction. So which t-test? We had 3. Which t-test are we using to determine this this result essentially? Do you remember which 3 we had? Which 3 t-tests?
Like the upper, is the 2/3?
We had the paired sample t-test. We had the the independent sample t-test, and which one more? We have one more.
Dependent.
The one sample t-test. So we have the dependent, the independent sample t-test, and the one sample t-test. And what did the one sample t-test do again?
Compared the scores to the population mean?
Yeah, it compared your average in your sample to a population mean, or exactly it's phrased as a population mean, but actually you can test it against any value that you want, of course. So what we are doing here, after we transformed our correlation to a t-value, we're just testing it against a population mean of 0, because we know from the t-test that it's always that assuming the null to be true, the t-value would be 0. So we're testing the t-value to 0. Does that make sense? You can also say if it doesn't make sense, right?
No. Could you repeat that, please? Thank you.
So we have a correlation value R. We transform it to a t-value, and we test that t-value in the same way that we've done in the first block with a one sample t-test. And we check if the t-value that results from our correlation significantly differs from 0.
When we have a correlation of 0.6, isn't there also like a scale deciding on whether a correlation is like good enough? Let's say 0.8 would be sufficient without running it through a t-test.
Yeah, sure. Of course, you can say something about the size of the correlation, and looking at these plots, we can see what's going on here. And a correlation of 0.6 is well, a bit high, not very high, but it's a bit high. But that's answering a different question, right? So the question that is posed and also run through these analysis is it a significant correlation? Is how likely or how unlikely in that sense is this correlation if the null were to be true? If there were no effects, if there wasn't in actuality a difference between IQ and or there wouldn't be a relation between IQ and grade, what would be the probability of finding such a correlation, or more extreme, if that were true? So you're essentially reiterating the null hypothesis testing, where you just say, well, I assume nothing to be true, and how probable is that if I assume nothing to be, how likely is the value that I find if I assume that in actuality there weren't supposed to be any differences.
Okay. Yeah, I'm getting closer to it.
Good.
Yeah, thank you.
So we have the t-value here, and based on those we can use the one sample t-test, where we essentially can apply the visualize function again. So we're doing that here. We're doing a two-sided t-test where we use the visualize function for the t. We've calculated our t-value. We look at the minus t value and the positive t value. we use the degrees of freedom of n minus 1, and we select the section to be tails, so to look at both the sides. And what we find is that our correlation of 0.62, which yielded a t-value of minus 5.4. So the probability of a t-value of lower or equal to minus 5.4 plus the probability of a t-value of higher or equal to 5.4 is 0.000000152. So my p-value is lower than my alpha level of 0.5, or even if I would be a bit more critical, such a p-value is highly significant. So it's such a value, assuming that there's nothing going on, is highly improbable. So therefore we reject our null hypothesis. Exactly, and it differs from 0. That's where it's tested against. Okay.
So a quick question. What does significance entail here? So does it mean there is a correlation if it's significant, or does it mean that the correlation is significant, or?
Yeah, that's a good.
I'm a bit confused.
It's a good question. It usually is used in the sense, oh, there is a correlation. Point. That's it. So if it's significant, there is a correlation. But as we've been critically looking at what the meaning of the Neyman-Pearson null hypothesis testing is, you could be more critical about this. So you could say, well, I reject the notion, I conclude, and that is what we've been talking about in this course, we conclude to reject the null, assuming, and that is our conclusion based on our set of rules that we set up and our criteria that we use to determine this, to come to this conclusion. So in practical sense, yes, of course, we use this. We see that the t-value is significant, and therefore we say, well, okay, there's probably a correlation. But essentially, we don't have a clue of what actually is going on. We're just rejecting the null. So it's a practical answer. Yes, there's a correlation, and there's a more philosophical, a fundamental question of what are we doing, what are we saying with rejecting null hypothesis? Well, we're just rejecting the null hypothesis. We're not accepting anything else. So, okay, it's time for coffee, right?
Yes.
Yes.
Yeah.
We'll continue a quarter past, and then we'll be back. See you in a bit. Welcome back, everyone. You get your coffee?
Yeah, did you?
No. I'll get it in a sec, I think. Yeah, great, thanks, dear. Got it.
That's adorable.
Yeah. Okay, here we go. So we've covered the correlation. What we're gonna do now is see how this correlation can be used to get to the partial correlation. So what we've seen up until now in the previous year, year 1, you also ran the correlation. But with the partial correlation, we are essentially doing the same thing as we've done with, for example, in ANCOVA. We want to know what the relation is of one variable. What the relation is between two variables. So, for example, we want to know what the relation is between x and y, while essentially correcting for some confounding variable, in this case z. So we want to look at, in essence, as a Venn diagram. You can view it in this sense, where we essentially take out the overlap that the confounding variable, that the covariate has on the relation between these two variables. Now the difference between the covariance analysis is that within the covariance analysis we actually, well, first off, our independent variables were a category, as when we use the partial correlation, we're looking at continuous variables. So that's one difference. The other difference is that an ANCOVA is actually, well, a linear model that you're running, just like we'll see in a bit when we go into the regression analysis. Whereas the partial correlation is using the correlations that we have between all these three variables to take out this specific part. So it's not essentially, you're not modeling, you're just using the correlation values to come up with a corrected correlation value. And we see, yeah, go ahead.
You mentioned something about confounding and ANCOVA. Wasn't in the ANCOVA the other variable explained part of the unexplained variance? So it wasn't that, it was a confounding variable, right?
Yeah, but within the ANCOVA, you view the covariate as the confounding variable, so the one that you want to correct for. So that is the most essential thing that you do with the ANCOVA, and essentially you're here doing the same kind of thing, but not with linear modeling.
It's not clear to me how can the in ANCOVA how can that be a confounding variable if both explain different parts of the unexplained variance? You understand?
No, I understand. I understand your question, but it's a general question about linear modeling. So even if you have a regression model with a couple of predictor variables, this goes in the same lines of reasoning. So being a covariate is not about explaining and having unexplained or explained variance. It's about taking the influence of that variable out of the equation. And so
okay,
it's not more mystic than that. It's just you have some variable that influences the other, and you want to take that out to see what the relation is between your dependent variable and your independent variable. So you're using that covariate in a sense, and setting that value of the covariate to 0 to know what the relationship is. But we'll be going into the multiple regression next week, and I'll try to make a link between those two, and this might make it a bit more clear what that relation essentially means, and what it and the fact that what it means to call it a confounding variable, because the term confounding variable is just something that is a nuisance to you, because you don't want to have it. You don't want it to skew your results. You want to take it into consideration and leave it out. But well, you could also have other hypotheses that don't require you to call this a confounding variable. But we'll leave it at this for now, and I'll try to make the connection next week. So if you look at this equation, first thing you see, this is not a linear model where we don't have beta coefficients, we don't have an error term in here. The only thing that we have here is correlation values. So where you would normally have just the correlation between x and y, that would be the correlation between your two, variables that you're interested in. Now you subtract the multiplication of the relation that x has with the z variable and the relation that y has with the z variable. So if you take those two parts out, then you're essentially reducing your initial correlation value that we have. And we have to divide this by, and now we're seeing that r squared popping up again. The r squared meant the explained variance. So if you see formulas like this, 1 minus r squared, it means the unexplained part. So the unexplained part between x and z multiplied by the unexplained part of y and z is the part here that we use at the bottom. So if you apply this, you will get the partial correlation. So it means the relation between x and y corrected for z. So that's not that difficult in a sense. When you have to do this, you can easily use the correlation function for these things. And if you run this analysis in SPSS, you can just assign your variables and run the analysis, and you will get your partial correlation. And so one thing that is, of course, of interest is what happens to the to your original correlation if you correct for this extra variable. So in SPSS you can apply the, I think it's called something. You can select that you want to also see the initial correlation, and that's useful because it will show you that in what amount your initial correlation is reduced in that sense. So now we've got all three of these correlations, and then it's a question of applying the numerator and the denominator, where we have the denominator where we have the initial correlations, and we subtract the multiplication of the correlation between x and z and y and z in this case. And we have the unexplained variance for the denominator that we use. So applying those two will land us a correlation of 0.66.
The previous slide data frame, what was that? The function?
Which one?
Data.frame. It's a no. Here in the green. Up. The other slide, previous slide.
Yeah.
In green.
Data frame. Okay. Yeah. Sorry. Yeah. It's putting these three variables in a table. So this, what you see here, is the data frame that we've created for these three. So the columns are the.
Okay, so 3 columns.
Yeah. It's the same as you use the cbind function sometimes, maybe. So we end up with essentially a corrected correlation, the partial correlation. And what we've done is, and I might not have made that too clear in the example. So we're looking at the relation between grade and between IQ and grade, while correcting for motivation. So in my simulation above, I also added the motivation as a factor. So now our partial correlation is the relation between grade and IQ, where we correct for the amount of motivation that we have. So we partial it out in essence. And that results in a partial correlation of 0.66. And this, as it is just a correlation, we can calculate the t-value again for this correlation and test if this t-value is significant or not by using the visualize t function. And again, here we find we find a significant result because, well, we have a t-value of the probability of a t-value lower or equal to -6, and the other side higher or equal to 6 is very low, 0.0, lots of zeros, 7 zeros. So we use this, apply this, and then we have our partial correlation.
And how would you interpret this in words? Meaning,
yeah, so
it's still a correlation, but
yeah, it
a lot more.
No, it essentially is a correlation. So in words and in research paper, if you're interested in these effects corrected for, then you frame it in those in that terminology. So you would say the relation between IQ and final grade for your exam is this and this when we correct for the amount of motivation. So we're partialing out the motivation part. So that's how you would frame it, and that's how you see it framed a lot of the time. Yeah?
Yeah, I'm just trying to wrap my mind around.
Yeah, these are hard things because we have a quite a vivid sense of what a relation between two variables is, but taking some parts out makes it mind-boggling, right? What helps is just to look at these Venn diagrams. So if we have the relation between x and y, and we want to take this part out, then what are we left with in a sense? But this is a generalization of this notion. Okay. Here we go. The regression with one predictor. This is not new. You've ran through this entire analysis in year 1. So I'll cover it, but it's mostly laying the groundwork for the multiple regression where we will be going into next week, and expanding our models to moderation analysis and so forth. So I'm coming back to this notion that field always refers to that we can predict, or we have the outcome that is a function of the model plus error, where in a sense the less error you have, the better your model is. And within a linear regression analysis, your model is the linear your model is the linear regression. So everything that you write up here is the model part. So field always uses this, but formally it states that your actual score, and I meaning that it's an individual again, so the score for a specific individual is the result of an intercept plus a slope, or a weight. You could also call it a weight. So this is a number, this is a number. It's multiplied by a specific score for the same individual, it's the same person, and you have the error term for that specific individual. So essentially what we've done in one of the first lectures, or at least in the first block, was that I asked you to look into each other's pixelated eyes and make predict the intelligence of the person next to you in Zoom. And you could view that in the same way, where your model is your expected score for that person, but the person next to you actually has a certain IQ score. So if you are off, then that is the residual, the error that you have. And instead of doing just a simple model or an intuitive model as to look at your neighbor and estimate their IQ scores, you can formalize this and make it more explicit. And we talked about it then already. We said, well, can you argue for some things that would make you think that the person next to you has a higher or a lower IQ, and then some of you came up with the fact that the next person next to you, that you know him or her, and that the person is very motivated or studies hard. So there are factors involved in this predicting process, and that is what we formalize with such a regression model. So one thing to take note of is that these betas, they represent the population parameters of these beta coefficients. Whereas when we run the analysis and we do them in SPSS, we get B's, which indicate that the thing that we get out of our analysis software are the estimations of those parameters, which also has an amount of error involved. But formally, this is the model. Okay. So if we look at the outcome versus the model, then I've plotted a few different relations, and what you see here is on the x-axis is the model, the expected value, and what we see on the y-axis is the outcome. So looking at the expected results, the model, only the model, and the outcome. So if we do that, we see for this one that if there would be a one-to-one relation between what you expect and what the actual outcome is, that would mean that all your expected values would be essentially the same as what your actual scores are. So if in such a situation you would find a correlation between the model and the outcome to be extremely high, 0.99. And if you would square this, then you would have the proportion of explained variance, which is also very high. But this is never really the case. You always find a certain amount of error. And so what I've done here is just to try to make you see, visualize the relation between model expectations and outcome as a relation between two variables. In a sense, this is just a scatter plot, but also showing what correlation is related to this. So this is just a simple, the same correlation that we've been talking about in the first part of this lecture. But now we use the model expectations as one at one axis, because this can be a bit confusing, right? Where you think of, especially when you go into multiple regression, where you have a lot of predictor variables, you can also always get to one expected value, because your model as a whole, with everything you put in it, will predict the outcome, and that's just for each individual, just one number. So you can always plot your model expectation against the actual outcome, and that is what I've done here. So this has a correlation of 0.49, 45, and if we square that, we only have 20% explained variance, where here we have a little bit higher correlation with about half being of the variance being explained and going up to the right. Now there are a few assumptions, and there are field covers a lot, and you just read those assumptions, but I wanted to pick out two that are that need some extra explanation. So I have the sensitivity and the homoscedasticity selected, and let's see, yeah. So for the sensitivity, it means that such a regression model is very sensitive to outliers. So, for example, if you look at this plot, you see that you can fit a regression line in such a plot, but there are no outliers. Where if there would have been an outlier, in the sense that our model expectation thinks it's very high, but in actuality the score for this individual would be very low. So if a point would be at this point we would have a score for someone, then it would disrupt your linear equation. So what is done in regression analysis is that we look at extreme values, so extreme residuals. And with residuals we mean scores that deviate, that the difference from the expected score and the actual score are very high. And again, if we don't standardize this, it's hard to determine what is high and what isn't. So what SPSS does for you is it provides a few standardized ways, standardized residual values, as the Cook's distance, the Mahalanobis distance, the leverage, and they're all essentially diagnostic tools that can help you find values that are very extreme and therefore disrupt your linear model. And you could think of this as as being a bit of a cherry picking, of course, because you're saying, well, everything that doesn't fit my model I take out, and so you have to make clear what your selection criteria are when you write your paper. So if you really need to take a few out because these residuals are very high, then you just write this down. Then you just state that, well, based on the Cook's distance, we found two observations that were too extreme, and we opted to not include them in the model.
But then that's a risky thing to do, right? Because in the end, there is randomness in your sample, so maybe those outliers, those represent some values that are actually part of the population or represent some part of the population. So
yeah,
taking them out could always mean that you are, like you mentioned, like you're cherry picking. So
yeah, I understand where you're coming from. But going further into this notion, you find this outlier in your sample, and one of the assumptions that we hold, not just for regression, is that your residual is normally distributed. The error that you have is normally distributed. So if that is the case, then such an outlier should also be available at the other side of the spectrum, right? So
yes,
if that holds, if that notion holds, then that would mean that it would average out. But based on this specific sample and the fact that you didn't find such an outlier at the other side, which is of course also highly improbable, you can justify in that sense to take this person out, because if you have a regression model that looks like this and you have an outlier here and an outlier there,
yeah,
then the regression model will stay a bit in the middle. But if you don't have this observation, then it will shift. Yeah. So in that sense, you can justify the decision for that matter, right?
Yes.
Okay. So here you have an example of this. So I have the model score standardized in this sense, and the outcome.
We don't see the screen.
Oh, sorry. Yeah. The model scores are standardized and the outcome. The red line is the actual regression model. No, the blue line is the actual regression model. But if you look here, we have an outlier. Someone that at we expect this person to score 2, but in actuality, the outcome for this person is -2. So this is an extreme outlier, which reduces our explained variance for our regression model to 83%, where if we take this one out, we will get the red regression line, where we have a correlation of 0.99 and explained variance of almost 100%. So you see, if you have such an outlier, it really disrupts your regression model, and it is justified to take such outliers out of your data set for analysis. But always report it. Don't take it out without reporting it. Okay. The other one is homoscedasticity, and essentially we've talked about this concept already, because it is the same. Essentially the same as the equality of variance. So within the ANOVAs that we've performed, we said, well, the variance needed to be equal across the different groups. For example, you wanted to measure intelligence, and you had males and you had females, then the variance of those two groups needed to be the same. So our independent variable there was only had 2 categories, but now we have an independent variable that has essentially an unlimited amount of categories, because it's a continuous variable. And even in that sense, the assumption of homoscedasticity is that the variance at each level of that variable should be essentially equal, or somewhat equal in that sense. So the way you can look at this and view this is that the residuals, or the variance of the residual, should be equal across all expected values. So instead of looking at the categories, you could use the residuals. So if it's one of the assumptions that the error is normally distributed, then the notion of the equality of variance would hold. But there is no test for this. It is only eyeballing. And the way this is done is that you can make, or SPSS can make, a scatter plot for you with the standardized expected values. So those are the expectations of the model by the standardized residuals. So on the one hand, on the one axis, you have the expected score standardized. Standardized meaning having a mean of 0 and standard deviation steps of 1. And at the other side, you will have how much you're actually off. So the difference between your outcome and your expected outcome. The difference between the outcome and the model. Also standardized. So if we do this, then you will get a plot, and if the dispersion of the dots is centered around 0 and a little bit in a circular form like we have here, then this assumption holds, the assumption of homoscedasticity. So SPSS provides such a plot for you with the Z-pred and the Z-predit, which means the standardized from Z and predicted value versus the standardized residuals values shown here. And in this plot, I've also added the 0 line, so you can see where the middle is, and I also plotted a big red dot in here to eyeball if it's circular in form. So what SPSS sometimes does is that the scaling of the x-axis is not the same as the scaling as the y-axis. So that means in SPSS it could be a little bit oval instead of circular. But if you read the chapter on this in field, if this assumption does not hold, you will see quite extreme results where the dots are, for example, more in a cone form, or they're arched, and those kinds of results indicate that the homoscedasticity assumption does not hold. So you in SPSS, and it's done. We'll do this in the weekly assignment. We will ask you to calculate or to make these kinds of plots with the predicted and the standardized residuals. And yeah, it's just eyeballing. There's no there's no test for this to see if this holds. Okay, now for the actual regression analysis. Again, I'm simulating the results here, where I want IQ scores this time to predict the grades. So I'm turning it around. So let's see if I can have a model where I predict the grade based on IQ. I put in the beta coefficient of 1, beta 0 of 1, that's the intercept, and the slope of 0.04, which is not that high. And create a data set based on that. So what you would find if you would not simulate this, but really get data from your experiments or your questionnaire. I'd have the grades and I have the IQ scores here, and those two variables I can use to run a regression analysis. So the thing that I want to determine is if I have all the grades and if I have all the IQ scores, what are the beta coefficients B0 and B1? So I know what the regression model is. So for a simple regression analysis, as we do now, we can calculate these beta coefficients. But when it gets more complex, it's not feasible anymore to do this by hand. And this is the thing that statistics software do for you. SPSS determines these beta coefficients. And essentially tests if these beta coefficients are significant or not. So let's first look at the first one, the B1. So that's the regression, the slope for IQ, and you should see this in the same way as you just had with it's the same as y is the value y is equal to a multiplied by x plus b. So it's just the equation for a line. So what we need to determine this is the correlation between x and y, and we need the standard deviation of both y and x. So if you apply this calculation, you get the value of the slope in essence. Well, and that's not that hard because we only need the correlation between grade and IQ. We need the standard deviation of grade and we need the standard deviation of IQ. So applying this in this formula, we will get the beta coefficient, and we see that the thing we actually simulated. So we put in a beta coefficient of 0.04, and we don't have a lot of error, just a little bit. We actually are able to recover that result. So based on our simulation, we can actually find this beta coefficient. And if we have B1, then B0 is just around the corner, because to get to B0, we have to subtract the B1 that we calculated in the previous step, multiply this by the mean of X, and subtract that part from the mean of Y, and that will result in the B0, which is the intercept. So if you have a slope, we just determined what the slope is. If you have a slope on an x-axis and a y-axis, we've determined the slope, and with the B0 we've determined where, on which height of the y-axis we need to place this slope. And that's B0, the intercept. So if we've done that, we find that it's 0.41. Was that what we put in here? Let's see. B0, that's a bit off because we put in 1. So that happens with simulation and where you introduce randomness. So our model is able to recover our B0. So in terms of slope, what do we find? Well, we have the zero, the slope is the slope of this line, that's B1, and our B0 is the point where our regression line hits the y-axis if the x-axis is 0. So that's about here. So we can zoom into this a bit. So if we only look at this part, the slope is determined by, is essentially the angle when you have one step in on the x-axis, and the part that we're going up, that's the angle that we have for this slope. So that is the part that we're looking at when we're determining B1. These two beta coefficients, they can also be tested if for significance, where we again just apply the t-test. And what kind of t-tests are we using here? If you look at this formula. Anyone?
One sample t-test.
Yeah, I saw it in the chat, right? So we're putting in the beta coefficient, we're subtracting our mu, our expected beta coefficient, which of course is 0, assuming the null to be true, and we subtract it by the standard error of that beta coefficient, which yields us the t-value, and we can use that t-value to run the visualize function and to calculate the probability of such a t-value, or more extreme, assuming the null to be true. So we do that for the B0 and the B1, and we get two t-values, where at one point we must consider what is relevant. So if you look at this, these two t-values, which one in your opinion is relevant and which is not? Which t-value do you think is relevant and which do you think is not relevant? For B0 or B1?
B1.
Yeah, exactly. B1 determines the relation of your two variables, where B0 only determines where to put this thing in relation to the dotted, the cloud of dots that you have. So this is not an informative parameter to look at. So most statistics software provide both, but you're always interested in the one that is related to your actual parameter, to your variable that you're interested in. So using the visualize function, you can I first provide the b0s to determine if this is significant. Well, this is not significant, but it's irrelevant because we're not interested in where the line hits 0. But for b1, this one is of interest. We do want to know what the relation is between those two variables. And we found a t-value of 6.4. If we look two-sided, if we test two-sided, the probability of finding a t-value equal or less than minus 6.4 plus the probability of finding a t-value higher or equal to 6.4 is less than 0.00, a lot of 9 zeros. And so this is highly significant, this result. Did you expect this?
Yeah, because the data was generated.
Yeah, the data was generated, but our intercept for B1, let's see, it was quite small, right? Sorry. Here we have it. It was quite small. So if we have to, of course, make a t-value for it, but the slope is not steep. It's quite flat. But so even with such a flat slope, we can find significant results. So that's something to consider. That even if your slope is close to 0, and it tests based on 0, it can still find significant results. But especially if the sample size is very large. So again, don't just judge on the significance, but also look at your data, try to interpret this, and look at the effect size that you're interested in.
Can you perhaps reiterate or restate what the purpose of the test? So we looked at B1, and based on finding a significant result, we can conclude what is the conclusion?
Our B1 determines if our IQ actually is part of explaining the grade. So we're doing regression analysis to determine if we have predictor variables that actually explain the outcome variable. And in this case, our outcome variable is grade. And the question is, can we explain, the outcome variable is grade, and can we explain grade by IQ? And if the beta 1 is significant, then that indicates that our IQ is a variable that has a strong relation, and if it's positive, of course, a strong relation with the outcome variable.
So basically, we're looking at finding a model or finding a B0 and B1 that can generate a model in which the grade is explained based on IQ.
Yeah, I would not state generate, because the data that we actually get from analysis is the thing we have. But given the data that we have and running such models, we can determine if this is a significant contribution to explaining the variance of our outcome variable. Now, if we apply this B1 and B2, we now have the actual grade, which is in our regression model predicted by IQ, and that model results in an expected value for grade that I've shown here as the model outcome. So based on this IQ score and the regression model, we think that for this person, your grade score will be 7.2, but it actually is 5.75. And for this one, we think it's 5.82, and in actuality, it's 7.61, and so forth. So we see that we have model expectations, we have actual outcomes, and the difference between these two, again, is the residual, is the error. So how much are we off with our predicted model? So if we have a good model, these two values should be very close to each other. And if we have a bad model, on average, of course, these values should not be close to each other. So we essentially can compare our outcome, our actual outcome, to our expected outcome. And that's why it has a hat. So if I plot these, then I have my model expectations set apart. So using IQ, I expect the results, the expected grades to be this, and in actuality they're this. So you see, it's fair, but it's not really high. So I'm quite off a bit. So if I look at the difference between what I expect and what I actually have, I get the error. And you see, for each and every one, I'm off quite a bit. Sometimes not, but it indicates that our model is not optimal. So in terms of the relation between what you expect and what you actually have, it means that as they are just two variables, just like when we've done with the correlation, we can just calculate a correlation between this. So just using the correlation function on the model expectations and the actual outcome, the actual grades, I can see what the relation between these two are. So what is the correlation in this scatter plot? And that's only 0.5. Well, if it's only 0.5, then the explained variance as is squared, the squared value of this is only 25%. So it's not a very good predictive model. Yes, IQ is a significant predictor in the model, but the model as a whole is not very informative in that sense. Well, in the last part, and then I'll stop, in terms of explained variance, you can again plot all the participants on the y-axis, plot the actual grades as the numbers, and plot the expected grades, which I've done here in red. And that will mean that in terms of explained and unexplained variables, we have the same as we've done with analysis of variance, where you can decompose each outcome variable into an unexplained and an explained part. And that is what we use for our results. Okay. Finally, you can test if your model predicts better than just using the average. And the thing that you essentially get here is essentially the relation between how much is explained, red parts, versus how much is unexplained, what's left over. And that is in essentially, again, just an F value. You can get there through a different route, of course, because now we're using the correlations, but this is exactly the same as what we've been doing with calculating the F values in the ANOVAs that we've done so far. So that is essentially, again, a signal to noise ratio. And on that, I will test that in an F value. But now we're done. It's time. It's past time. 5 minutes over. Sorry. Okay, I'll stick around for some questions. And good luck with the weekly assignment. I'll see you next week.
Thank you.
You're welcome.